So how do you use the eFMI facilities in Dymola? We provide everything in terms of a library called Dymola Embedded. And what you do essentially is you go to the Tools ribbon, and there you have this little eFMI button. And if you click on it, then you can load the libraries. Press OK, and then the libraries will be loaded. And then what you see in the package browser are 4 libraries that are loaded. 2 are from the Modelica Association. That is the eFMI library, which we provide from the Modelica Association project, eFMI, which is mostly to help you with tables. Because in the MSL, tables are implemented by terms of some C code, and this is external code. We cannot just embed this on our embedded device. So we provide in the eFMI library table adapters. You can use these ones instead of the MSL tables. It's very simple. If you do that, then we can guarantee for the embedded code generation that we will properly use proper code, the production code generator, to enable tables and interpolation. The second library is the eFMI test cases library. These are the official cross-checks that we use with a lot of examples. Examples more like unit tests, really complex things like a controlled slider crank, or also our drivetrain example, or a steering reactor for chemical reactions. And this one also comes from the Modelica Association project, eFMI. And then we have 2 libraries that are dedicated to Dymola. The one is Dymola Embedded. This is the interface we are going to use for generating eFMUs from Dymola. So it provides the means to configure the eFMU generation and generate the various eFMI containers. And then we have something called eFMI test cases embedded configurations. Well, these are from us prepared configurations for the test cases of the eFMI test cases, so that you can just straight away generate and test them. From Dymola, you don't have to do your own embedded code generation configuration. You can do that, of course, it's not a problem. This enables you to do using eFMI facilities straight away. This one also already contains a configuration for this M04, but we don't want to use this one. We want to do it from scratch, as if you're really a completely new user and you have to configure everything yourself. And to do it from scratch, you create a new package that extends embedded configuration. So in Dymola, via the file menu, you make a new package. Please name it just my M04 eFMU. And once the package is created, you go to the text layer, and there you extend from Dymola embedded configuration. That's the only line you have to add. Extends Dymola embedded configuration. In a semicolon. And then you can switch to the graphics ribbon, and then you should see this thing here. So from this diagram, you can configure the whole embedded code generation stuff to generate eFMUs. So from here on, it goes on graphically. I call this a eFMU generation configuration. Now, we configure our code generation. So you can double-click the Gallic code generation, the model configuration, and there you can pick the model name. That is the model for which you want to generate an eFMU. In our case, this is our controller. You have this little tree diagram thing. If you open this, a menu comes where you can pick the thing. And of course, you pick from the eFMI test cases, from the M04 drivetrain torque controller. From the controllers package, you pick the controller. And then you confirm. And then another thing that is interesting is by default, the Gallic code we generate is obfuscated. This is the default. To be as defensive as possible, because maybe you don't want to share too much information about your controller, because the Gallic code can be easily linked back to the model. And you may not want to share details about your model. But in our case, this doesn't matter. So you also double-click the code configuration and say you don't want obfuscation. And then you have, of course, to configure the inline integration scheme. So in this case, you double-click the integrator configuration, and the sampling period is half a millisecond, and then you click Assault or the explicit Euler and do OK. If you did all these things, you're settled. In theory, in this generation configuration, well, not only in theory, in practice also, you could change code generation for the software production engineering. But there is no default configuration already active, because you have software production engineering available in your setup. And the default configuration is that we will generate for 2 types of floating point precisions. 32-bit floating point precision, 64-bit floating point precision. And the second thing, for the binary generation, we will generate for the Intel instruction sets, but for 32-bit and 64-bit binaries. So this makes altogether 4 binary codes. So you don't have to do anything here. Don't configure the software production engineering configuration. It's fine. This is. That's the default. Since you inherited from this Dymola embedded configuration, you get a lot of generation functions where you can do stuff. And they are all using this configuration that you just set up by default. You can always, when you call one of these functions, interactively change it if you want, but the default is this configuration. And the generation things you can do if you press this little extends entry in the package browser, and then you see this stuff here. This is the things you can do. And the activities for the code generation, they are grouped in the different eFMU containers that we have and things we can do. So we can generate Galley code, that's an algorithm code container. We can generate behavior models from existing experiments. We can do checks of our production code. We can generate production code. We could check it with MISRA checks if you have a CPP check available. And we can do stuff for the binary code where we kind of generate a little stub in Modelica that we can drag and drop it. And then this component in your Modelica models will just be the eFMU, connect in and then take the outputs. And in fact, the production code is used, like we're used from the eFMI. And all of these things can also be conveniently done together with this build function. If you don't look at the individual ones, you do it all in one step. And there are also functions in the tools ribbon, this eFMI button, where you could generate for a whole package with hierarchy everything. So what we want to do now is we want to generate our eFMU. And basically, you go to this build function here, you right-click it, and then you can call a function. You do that, and then you just press the OK button, and that's it. And this will generate you an eFMU for this example with the algorithm code container and the production code container. Algorithm and production code containers and the binary code. You don't have to search where is this eFMU generated. You can call this browse code function, right-click call function, and it will open in the Explorer the directory where the eFMU is. So if you open what was generated, you should see all these things except this B model. It's a behavior model. We didn't generate it yet. And there's a lot of stuff. This is the algorithm code container. Then you have binary code containers or the different floating point positions and different instruction sets. And then you have the two production codes for 32-bit and 64-bit floating point positions. And you have this manifest XML, which is like eFMI. So this one lists all the different containers. And in principle, you can dig into each of them and look into them. You can see this cross-referencing between the manifest that I described before. You can look at the Galley code and see, oh, this is quite readable representation of an algorithmic solution. You can see a lot of things going on. There is one last thing you can do if everything is generated. You can now also check the general production code for MISRA compliance. I can't distribute you the CPP check premium. For that, you need a license. We don't have that. But the open source CPP check has also MISRA, very outdated old MISRA checks, and not so nice, but it still does something. And you can do that if you open this production code thing here and do check code. And then what will happen is it will check the CPP check and with Clang Tidy and open the Clang Tidy reports and the CPP check reports in your browser as HTML with nice rendering, syntax highlighting and stuff. We are very strict. The checks we configure in such a way that every rule is checked, even if it's optional, if it's not a mandatory rule. We check everything, also for the Clang Tidy, as strict as possible, which is completely ridiculous. So that's really everything you can squeeze out of these checkers. And for the, let's say, the MISRA checks, there are things like, yeah, this function is not used. Yeah, but we have to provide it because the interface is standardized, so the function must be there wherever you use it or not. So we did the generation of the eFMU, and basically we generate everything we want. The question is now, what can we do with it? And the main thing we want to achieve now is we want to do a software-in-the-loop simulation with whatever we generated. For a software-in-the-loop simulation, you can imagine it like this. You have an existing experiment in Modelica, in Dymola, and you can run it with our offline simulations and play with it. And there's also the controller. And now you would like to replace the controller instance you have there, which is complete Modelica code, with the eFMU, so that you use instead the production code we generated. And then you want to see, does it do the same? And that's a software-in-the-loop test. So you use the production code that was generated for an embedded system, and you try it with your original test scenarios to see if it does the same. And to do that, you can think of a similar way like with eFMI. If you import a eFMU in Dymola, we will generate a little Weber model in Modelica, and that Weber model you can drag and drop, and wherever you drag and drop it, you get an instance of the eFMU, and you can use it and connect it. And here we do the same. We will generate a little Modelica wrapper that links to the external C code, which is the production code of the eFMU. And then when you use this Modelica wrapper, you're in fact using the production code. And you can generate this Modelica wrapper if you go to the binary code, and then you pick this build binary stub, right-click it to call the function, and just OK. You don't have to configure anything, you just do that, and that will generate you this little wrapper. There's a new package called like your eFMU configuration, my M4 eFMU, eFMU SEL support, and it contains this binary stub model, which is this proxy that links to the production code. This stub does provide a lot of facilities, this generated package, that are interesting. So first of all, maybe you run into this issue in eFMI in the past. You have an FMU, you import it, okay, it's one instance. And then the same model, you add another instance of this FMU, and you simulate, and unfortunately the code that was generated uses, let's say, some global C variables, and the instances are not atomic, and they interact with each other, and what you get is complete simulation garbage. In best case, you get an error message, in worst case, you don't know what's going on. This will never happen with eFMI. For the software production engineering generated code, we guarantee this is atomic, so each instance has its own state. And that's fine. So you can do arbitrary many instantiations. The second thing is, for the stub that we produce here, it provides you all the floating point positions, 32-bit and 64-bit. It runs both in the background. It's only that you select one who will be used on the outputs and the inputs and for the computation. So you can also, if you simulate this with the stub, easily compare 32-bit floating point position with 64-bit floating point position of the production code. Usually in Dymola, whatever simulation you do is always 64-bit floating point position. There's no way to make Dymola simulate with 32-bit floating point. But here for this eFMU stub, you can compare. Another thing this stub does is it supports you all kinds of modification. So it will have the same top level parameters, so you can modify it. But on top of that, the parameters that have been selected for tuning as tunable parameters, you can recalibrate at runtime. In the same simulation, you can change the parameterization. You can also reinitialize. These are the functionalities that come from the Gallic block lifecycle. Then we also assert all the error messages coming from the production code. Because if you remember, I said in Gallic, every error must be handled, or it must be signaled to the outside. That's what the Gallic guarantees you. And of course, we can see, has there been any error signaled? So we can assert it. This stub will preserve the original interface. So multidimensionals stay multidimensionals. They are not scalarized away. If you have an input that is a matrix, it will stay a matrix. The in and outputs will be at exactly the same point. So you can really nicely replace your original controller model with the stub. It manages its own sampling stuff. You don't have to do anything about that. The sampling parent will be the one you use in the eFMU code generation configuration. It really just links to the production code. There are no other library dependencies or whatsoever or C code involved. And then another thing you can do, okay, you generate this stub, and now in principle you could start to write your own Modelica models and use this stub and define it this way, something where you can software in the loop the production code. But in practice, most often you already have experiments because you started with a full model where you have the plant model and the controller, and you did it all with Dussel and the normal offline simulation. So why shouldn't you just reuse what you have for the software loop test? And for that, we provide you facilities to generate it. And that works via this behavior model entry, where you have this build tests function. And the idea now is we use the experiment defined in our eFMI test case as reference experiment. So you open this function, you call the build tests, and then you pick the source experiment. In a source experiment, you pick in the M04 controller, for example, this controller explicit Euler closed loop. You pick that one, and then you just confirm, okay. And then what happens is we generate we call a experiment package, which is a new generated package, where you can do the software in the loop tests against this original experiment. Now, if you look into this generated package, it's interesting. If you double click the root of the package and go to the graphics view, you should get this view here. And essentially, you see in this view, in this case, we have only one scenario because there was only one instance of the controller. If we would have more instances, there would be more scenarios because each instance describes the expected in-output behavior. Then we have the possibility to define tolerances. And tolerances may not be always the same for every scenario. So You could define for every scenario individual by double-clicking this little thing here, or you can define for all the scenarios also at once using the default tolerances button. This is a way to define the tolerances. Then we have a function where we can build the behavior model container. So the idea here is that we do not only have this experiment package, but in fact, we can use this to build a eFMI behavior model container where we have the manifests and all the CVS reference trajectories. So that this experiment package is backed by the behavior model container. When you build a behavior model container, you can browse it to look inside, and you see it. So it's part of your eFMU. And then we have always exactly one test reference experiment. That is like our normal experiment from which we originate. We simulate it to produce the reference results. And we are using here a library called testing library that ships with Dymola. And this one is about much more than just eFMI. So you could also do reference tests of your reference experiment. For example, if you switch Dymola version. You get a new Dymola version, and then you just run the same thing and see, oh, does it simulate the same? Or did something change a little bit? That is in the normal offline Dymola simulation. And then we have, for each scenario, for each production code, defined an experiment, where essentially that very production code is software loop tested against the reference experiment. The first thing you have to do, you can leave that if you're curious, you don't do that. If you define zero tolerance, the test will fail. Because zero tolerance is zero tolerance, and every little change in the floating point operation and the order you do things will cause a difference. So this is really like insane. You will seldom have a scenario where this will pass. However, you can do that. But for now, what we do is we define the tolerances. So this controller has one output, right? So we define tolerances for the absolute and relative for 32-bit floating point position, 60 floating point position for the M motor. So you double click the default. Just this icon here, and then a dialog will open, and there you can set these tolerances. So I recommend you to set these tolerances. These tolerances will pass the test. You can later then change them to something more tight and see the test fail, for example, the 32-bit floating point. And then we have everything set up to build our behavior model container, because the tolerances go into the manifest of the behavior model container, because other testing tools want to know the tolerances that are acceptable. So to do that, you just call this build function. Right-click, call OK. And then afterwards, you can look into the container and see what was generated. Essentially, it will be, in this case, only one CSV directory file because we only have one test scenario. If you would have more instances of the controller, you would get more directory files. And you have the manifest that describes all the test scenarios, tolerances, how it's mapped to the CSV file, and so on. You can take your time later to investigate this, look into the manifest, how this links. This is the stuff you get. XML manifest with the test scenarios, the links to the algorithm code, which kind of things you have in output unit parameters, the variables, the tolerances, reference directories. After that, we can do finally the software to loop test. And that's very simple. You just pick, let's say, this first one here. This one here, that's a 32-bit floating point precision. You double click on this experiment, and then you simulate it. So double click this one, go to the simulation tab, press the simulate button, and it will simulate. And the result will be most likely, if you look into the commands window or simulation log, it will show you that it's a success, the simulation, and the test passed because we had a good tolerances. And it will also say you with what has been tested. But you can also plot this. For example, you pick this M motor, the match block, and there you pick actual reference for plotting. So the one actual is what the eFMU production code simulated, its output. And reference is what we expected from our normal offline simulation. An interesting thing is if you zoom in into this plot, zoom in, then you see a slight difference. And that is because what you simulated here was a 32-bit floating point precision. The reference was 64-bit floating point precision. So there must be some difference, but it's within tolerances. If you would tighten the tolerances and run the test again, you will see it fail, very likely. one question I often get here, if you have these funny names for the production code containers with this hash code at the end, why do we have such ugly names? There are a bunch of configurations you can do. And we collapse all the configuration computer hash code for them. That makes a unique name for the production code container. So the same configuration will be the same name. This is to avoid, first off, any clash if you generate with different configurations that you end up in the same directories. And second, if you use the eFMI export, also Dymola, you know if we start to generate names that are unique based on the configuration, you get a path length of 500 and higher, and then you die. So in Windows is the way to avoid the max path length issues. But how do you know which production code containers which? I know it by heart from the hash codes, but you don't have to know it by heart. If you look into this SEL stub package, there's something like resolve code names and resolve code configuration. If you call these functions, you can basically select the production code container, press OK, and it will show you the configuration on the commands output. And then you see in the configuration, okay, that's my 42-bit one. Another way is, of course, that you look into the containers themselves in the manifest, because the manifest of the production code will tell you which floating point position it has. That's a little bit more cumbersome. We have here this general test SEL scenario where you can do a few more configurations, and there you can pick something that's called defining code. That is basically which production code you want to use for producing the outputs of that thing. So with this defining code, you could also switch the production code you want to use, and there are more things you can configure. So this was SEL testing. We are still talking about only generated stuff. The only thing you had to do here was to define the tolerances. And that's, of course, depending on your domain and scenario, what is acceptable for you. But otherwise, it's all still an automatic process. What we want to do now is even more advanced stuff. Now we want to do something where Modelica is lacking. And that will bite you on the butt. And it's very complicated. And that is we want to do online recalibration. So we want, while the thing simulates, change tunable parameters. And we want to do reinitialization. That is, while the thing runs, what happens if you have to restart the controller? Let's say another system part failed, and for that reason, we want to restart the controller. So reinitialization, input-dependent reinitialization. That is important, because in eFMI, you have the startup function that gives you a default initialization for everything. But you have reinitialize. That takes the current inputs to initialize. And the initialization code for a Modelica model can become quite complex. If you have like a steady state initialization, considering the current inputs, why is that important? Because you may, if you get a complicated controller, it's very tricky to find the right start state. Let's say we have something where we depend on temperature. It makes huge difference if you say default temperature is 15 degrees, and then you're in your car and the thing starts at 30 degrees. Then your controller is quite off with the initialization. However, the code we generate, we can handle the case because we do a proper initialization section code generation, the Galley code in Dymola, and then you can reinitialize at the beginning with the correct temperature. And then your controller starts off in the right state and it doesn't have to swing in. In the worst case, it never swings in. For that, I prepared you a recalibration example. And if you open that model, we have 4 instances of our controller. And these 4 instances, they are the untuned one and not modified. That means this is the default initialization of the thing. It has the parameters, have the values as they used to have. The inputs have their default values. Then we have a thing called parameterized. That is what you would usually have a Modelica if you do a modification on a model. So you change the parameters, right, via modification. In this case, there are 2 parameters changed, the CRES and the gain of the PI controller. This is a modification at the very beginning of the simulation, like you are used in Modelica and also Dymola. This is not an online recalibration. This is just a normal modification. Then we have a thing called tuned instance. This one is unmodified, so we didn't change the parameters, but instead, at runtime, at the later point for simulation, we will change to this very new parameter settings. That's a recalibration. And then we have a last instance that is tuned and reinitialized. That is essentially where we do the full package. So at a later point, we recalibrate, and at some other point, we reinitialize the controller. How does this work if we do the recalibration stuff? First of all, remember, all 4 controllers use the same production code, right? Because we want to compare for the same production code. This is given here in this defining code. You can set it, which production code. Then the series and the gain of the PI controller, they all switch to the same value, so to say, only at different time points. Some doesn't never switch to a new value. That is the untuned. The parameterized one, it will switch before we start with do-step, before we do simulations to the new parameterization. The tuned ones will, throughout simulation, switch to it. And the tuned and recalibrated will also, throughout simulation later, switch to it. And they all do the same changes. The CBS changes from 4110 to 2710 at the very beginning or throughout simulation, and the gain also. How are the runtime values provisioned for the recalibration? We have this CarPI and the CRES, and then we have a tuning bus where we put these new parameters, and then at some time point later, you see this is a step, so there's some time nothing happening, and at some point we recalibrate to the new thing. And for the reinitialization, when we reinitialize the controller, we have a Boolean timetable that at some point later says, oops, no reinitialize. This co-simulation step, it provides you this bus that you can activate that is used for recalibration. If you activate the bus, then you can tell which parameters will be recalibrated, and that one you just connect to the bus as a bus signal. So it's quite convenient. You see that the tuning is enabled by modification of the co-simulation steps by saying you want to tune and selecting activating the tune parameters via the configuration. So then the tuning bus connector is available, and now you can provide this via the tuning bus. So new recalibration parameter values are provided as runtime values connected to the tuning bus, and only tuning activated parameters have to be provisioned. All of this tuning bus thing is provided in this generated co-simulation package. So you can drag and drop this tuning bus from there. You don't have to write it yourself. You just drag and drop it and can use it. And in this case, we defined all this tuning configuration here in this tuning configuration instance of the record. And the reinitialization works like you double click also such an instance. You say you want to enable reinitialization, then this little stop button thing, as you know it from industrial environments, there's always this button if something goes wrong, press stop. So that thing pops up, and now you can connect to it. It's convenient. You also don't have to take care when is the sampling exactly happening. You just say at this time point, I want to do a reinitialization, and even if it's just a short spike, and then falls immediately, but you call a rising edge and then falls again, this step here takes care of that it registers that you want to reinitialize, and when the next sampling happens, it will reinitialize. So you don't have to worry too much about defining exact sampling times and stuff. Just do it, and then it reinitializes. And now you pick that model and simulate it. And when you simulate it, you plot this M motor. And then you zoom in this first interval between 0 and 1 second and 1.05 seconds. And if you zoom in, you see this kind of plot here. And this plot has four trajectories for the different controllers. There is the untuned one, there is the parameterized one, tuned and reinitialized one. And another thing you should plot is this recalibrated signal. That means when did we do the recalibration? And then you get these little spikes here, this here. Here was one recalibration happening, here was another recalibration happening. And now it's interesting. So what you can see in this plot, when do parameters and tuned plots align? When do they have the same trajectories? When does untuned align? Is the controller fast adapting in case of errors that require a system restart? For example, here you see the reinitialization. That is difficult because here we reinitialize the system, it goes back to its default states, and then you see how fast is my controller actually adapting to the current system state. That's the time difference you see between these two. That's an interesting kind of analyze, because it means if something goes wrong in your system and you really have to reinitialize, is your controller capable to adapt fast? And for the others, it's always good to remember that all controllers use the same production code, that the CRES and KI parameters change consistently. So if they change at all, right? They change, only the time they change is different. And here I wrote here when the reinitialization is. If you look at this is our tuned motor. So it starts with default parameters, and then we recalibrate, and then it continues. The green, in that case, is the untuned one, and you see they are different. Yeah, I think this is something you can take some time to investigate. Why are the graphs as they are? But the point that I want to show you here is the online recalibration is really working. So if you, while the system is running later on, recalibrate, it does a short jump, and then you get the new trajectory that is correct. And then I can ask you a bonus question, because I said at the beginning, this recalibration topic is something where Modelica is lacking as a language. And now we can ask the following question. Why can Dymola not generate? To be precise, it makes no sense. Behavior model containers with recalibration and or reinitialization test scenarios. Why is that not possible? Why can you not generate such behavior model container for Modelica? And this is a little bit a chicken egg problem. I will try to explain you. The concept of recalibration doesn't exist in Modelica. If you take your normal controller model, once the simulation starts, you can't change the parameters. Simulation runs through with these parameters. You can't change them. This is given. That's it. No, if we can't, and what would we do in Dymola if we want throughout a simulation run change the parameter? We make it input. But that changes completely the equation system. That's a whole different story. That has nothing more anymore to do with parameters. So if we put for this, then the thing is input generate eFMI, you make a completely different Gallic code. And then if we think about automatic generation of the tests, if we want to generate a recalibration test scenario, that's our experiment package. Sure, I can generate from the stub. But if I generate from the stub the software in the loop test, then my reference result is from that very same production code. That's useless. It will always pass. What I need is an offline simulation scenario, normal Modelica, where I describe a recalibration scenario such that I can generate my reference results, and that I can then compare against the SEO. And Modelica, the whole topic of parameters, constants versus final, is a topic where even experienced users fail to understand what this is supposed to do and mean. It's really tough. And we have the same recalibration concept in eFMI, and you can also not for avenues do this properly. Define a reference as software loop test in terms of I want to software loop test the avenue. So this is something where we would have to look into, but I can tell you there are many opinions in the Modelica design group for the language. And this is a worm of cans, a can of worms. But in eFMI, it's working. Last but not least, a few final touches. What you can do is you can export your eFMU as FMU now. What we do essentially is we run our normal export facilities for FMUs on the stub. And everything gets packed up, the binaries that have been produced for your production codes, embedded in the FMU, and then you can ship it to other FMU users. Question is, what happens to this defining code and tuning and reinitialization? Well, they basically all get just deactivated. Then you have this function to produce a script for Simulink. That is to import a production code container to Simulink. So if you call this from Dymola, we will produce a MATLAB script. And then in your Simulink environment, you take this thing that's called cfunction block. That is to integrate external code. You just drag and drop the standard Simulink block, run on it the script, and that will initialize this block to use the production code from this production code container. So parameters will be available that you can change them from Simulink. The inputs will be there, the outputs will be there. It will take the correct types from your embedded target, uint8 or uint8 16, 32 to 14 or 64 to 14 point precision. This is really that it interacts well with the Simulink code. And then if you add further blocks around it and connect them with your block in Simulink, you can generate for the whole thing code. And what happens there is the Simulink ERT, let's say, for an embedded real-time target, will generate for the other codes block, other code blocks code, and it will generate the required connection code to integrate your eFMU production code. But it won't change the production code itself. But what you get out of this is something where you can use the MATLAB Simulink environment to deploy on all kinds of targets that are supported by it. So you can essentially reuse your existing workflow if you use Simulink and go directly the last mile from the production code to a certain Simulink target, embedded target in the Simulink environment. And just do that and then deploy and you're settled. And then we have another new thing that is not available yet in Dymola, that will be in the next Dymola release in November. And that is we support the same thing for Arduino. So you can build an Arduino sketch, which means we take a production code container and build a sketch. And that sketch you can import in your Arduino IDE and continue deployment and stuff from there. And in that case, I mean, you somehow have to say how to connect in and outputs. We will generate you templates, which are commented code that tells you connect here the inputs, send there the results to the outputs. These are the possibilities for recalibration. And we will also generate you code for the timing, because the Arduino, I don't know if you used it, it's rather stupid, simple device. It executes code as fast as possible. So if your sampling is every 10 milliseconds and the code happens to finish the two-step if the sampling is every 10 milliseconds and the step happens to be finished after 2 milliseconds, Arduino will continue. So the virtual code runs much faster than the real time. What you have to do is you have to sleep it in between and tell it, okay, now you can wait. And this code we will generate such that it really does the right real-time execution. And of course, the other thing you want to test is, does my code actually compute fast enough? Not the other way around. I have a sampling period of 2 milliseconds, but the two-step takes 10 milliseconds. For that, we generate your code that you can easily test this by sending out to you how long did it really take to do a step. And then you activate once, check, is my Arduino powerful enough? Does it fast enough execute my code? Okay, then you deactivate it again, the preprocessor, and then from there on you settle. Okay, this finishes essentially this part of the tutorial. And I'd like to say this was advanced stuff at the end. So if you managed to do this, you did it like before. And we can go to the advanced demonstrators that